Here we look at more examples of linear transformation. So let's start with the function from the vector space R into R, given by L of x equals the absolute value of x. So remember that R, or in R as a vector space, the addition of vectors is the usual addition of numbers, and scalar multiplication is the usual multiplication of real numbers. Is this a linear transformation? So observe that if we take real numbers 1 and -1, so these are two vectors from the domain, the image of their sum is equal to the image of 0, which by definition is equal to the absolute value of 0 or 0. So this is L of 1 plus -1. Let's compare this with L of 1 plus L of -1. L of 1 is absolute value of 1. L of -1 is absolute value of -1. The sum is equal to 1 plus 1 or 2. So these two guys are different. So in other words, the first condition will never be satisfied for this function L. So L does not respect vector addition. So this shows that L is not a linear transformation. Here's another example. So consider the function L from R3 to R2, given by L of xyz equals the two vector xy. Is this a linear transformation? So let's see. Let's check the first condition. So given two vectors, x1, y1, z1, and x2, y2, z2 in the domain R3, let's compute L of the sum. L of the sum is equal to L of the vector whose components are x1 plus x2, y1 plus y2, z1 plus z2. The definition of L implies that this guy is equal to the two vector whose components are x1 plus x2, y1 plus y2. Okay, but this vector can be written as a sum of two vectors. Those vectors are the two vector x1, y1 and x2, y2. But this guy, by definition of our L, this guy is equal to L of x1, y1, z1, while this guy is equal to L of x2, y2, z2. So we see that L of the sum equals L of the first term, the first summand, plus L of the second summand. In other words, condition I in the definition of a linear transformation is satisfied. So let's see if the second condition is satisfied as well. So consider a scalar C and an arbitrary vector in our domain. So L of C times xyz is equal to L of the vector with components cx, cy, cz. We simply performed scalar multiplication here. Then we apply the definition of L. Okay, L of cx, cy, cz, according to this definition, is the two vector with components cx and cy, which can be written as the scalar multiple of vector xy by c. And because of our definition for L, this vector here is equal to L of xyz. So the second condition is also satisfied by our L. So we conclude that L is a linear transformation of R3 into R2. This map here is an example of what we call a projection map. So in this case, L projects the XYZ space into the XY plane. Okay? By removing or by forgetting the third component, we are simply considering the xy plane in the xyz space. So we are projecting into the plane. Okay, so consider now L from R3 into R3, defined as follows. So L of an arbitrary vector in the domain will be sent or will be mapped to the 3 vector in the codomain whose first component is the sum of the first and third components. The second component is obtained by taking the sum of the first and second components. And the third component is the difference of the third component from the second component. Is this a linear transformation? So we check if the two conditions are satisfied. So for the first condition, we take two arbitrary vectors in the domain, x1, y1, z1, x2, y2, z2, and compute L of x1, y1, z1 plus x2, y2, z2. So we just perform vector addition first, okay, before we apply our definition for L. Okay, so with x equal to x1 plus x2, y equal to y1 plus y2, z equal to z1 plus z2, this guy is equal to the vector with components as shown. First component is the sum of the first and third components. Second component is the sum of the first and second components. The third component here is the difference of the third component from the second component, following this rule. Okay, so we have to show if we must verify condition I, the ending in this equation should be L of x1, y1, z1 plus L of x2, y2, z2. So how can we arrive at that expression? So let's manipulate each component in this vector. Let us combine all terms with 1 as subscript and combine all terms with 2 as subscript. And then we split this 3 vector into a sum of 2 3 vectors. So you can verify that this guy is the same as this sum. Okay, so we're on the first term, we have all terms involving 1 as subscript. In the second, we have all terms with 2 as subscript. But if you compare this guy with this guy and this guy with this guy in the definition of L, the first and second terms here can be written as the image of x1, y1, z1 by L and the image of x2, y2, z2 under L. So condition I in the definition of a linear transformation is satisfied. Continuing, let's see if the second condition is satisfied as well. So take an arbitrary scalar C and an arbitrary vector in the domain, then compute L of C xyz. Okay, by definition of scalar multiplication in the domain, this is just L of the 3 vectors cx, cy, cz. So at this point, we may apply the definition of L. Okay, this thing here is equal to the vector with components cx plus cz, cx plus cy, cy minus cz. Again, we follow this rule. But observe that in this vector, each term has a factor c. Okay, so we can factor out c and then take out of the vector We can write this as the scalar multiple of the vector x plus z, x plus y minus z by scalar c. But this guy and this guy are exactly the same. So we can rewrite this as c times L of xyz. Okay, so we see that the second condition in the definition of a linear transformation is also satisfied. So we conclude that L is a linear transformation of R3 into R3. Okay? V and W are the same. No? So the domain and the codomain are the same. So we also call this a linear operator of R3.